Hello viewers, in today's lecture I will discuss about an important topic, catalysis, a topic that is interesting both to academic persons as well as to the persons working in industries, because catalyst is the backbone of chemical industry. I am going to cover the following topics one by one: a brief introduction, what is a catalyst, classification of catalysts, homogeneous catalysis, heterogeneous catalysis, then a simple basic theory called intermediate compound theory, and then I will summarize. So, catalysis is important. Why it is important? Because it is able to increase the rate of a chemical reaction. That we have mentioned during the discussion on reaction rates. We come across the factor catalyst to be an important factor that is used in increasing the rates of chemical reactions. The phenomenon in which a catalyst is used to increase the rate of reaction is called catalysis. The term was coined by Berzelius in 1836, but then we have a better description of what catalysis or catalyst means from the Chinese. Zhu Mi, which stands for the marriage broker. Yes, catalyst exactly does the job when the reactants approach them. The catalyst facilitates the formation of product. The catalysis was considered as black magic earlier. Reason being, certain substances when added to the reaction system were found to increase the rate of reaction. How, why, there was no answer. You add, if it works, well, good. If it does not, take the next substance. That was the approach called the trial and error approach. But then catalysis is emerging slowly as a science as we get an insight and on and about the surface of the catalyst. Although that is beyond the scope of this lecture, we must know that now catalysis is considered as a science. Why? We will not bother about it at this moment. There is hardly any industrial process where catalyst is not used. There are several steps, at least in some of the steps catalysts need to be used if the process is going to be economically viable process. Otherwise, the industry has to shut shop. Catalyst thus acts as I told you, backbone of chemical industry. What is a catalyst? How do you define a catalyst? Catalyst is an auxiliary substance which, when added to the reaction system, increases the rate of reaction without being consumed in the reaction. It is important, it is not consumed in the reaction. There are substances which also decrease the rate of reaction. Such substances are called inhibitors, or sometimes referred to as negative catalysts. Inhibitors are also important because they are able to prevent the reaction. If a reaction is undesired, we want to stop it. So, inhibitor can do that job for us. There are some reactions in which the product of the reaction itself acts as a catalyst. Such a process is called autocatalysis. Appropriately, the catalyst is generated during the course of the reaction. One best example that you have, and I think you have experienced that in a titration in the lab, the titration of oxalic acid versus potassium permanganate. You are told by the teacher, you warm oxalic acid solution, add permanganate dropwise initially, because the pink color does not disappear easily. But after a few drops of permanganate solution is added from the burette, the pink color starts disappearing faster. The reason being, MnSO4 that is formed as a product of the reaction acts as a catalyst. Therefore, this is a very good case of autocatalysis. How a catalyst functions? A catalyst increases the rate of reaction by providing an alternative path of lower activation energy. We have come across the term activation energy in kinetics. The kinetic energy possessed by the molecules helps them to overcome the barrier that we can see in this diagram. The diagram that we have, if you have an uncatalyzed reaction, the barrier is very high. Activation energy for the E uncatalyzed, where we are not using any catalyst, but the catalyst provides an alternative path where we have shown it by a dotted line. The energy barrier is now smaller. So, E cat, activation energy for a catalyzed reaction, is much smaller than the activation energy that we have for an uncatalyzed reaction. How it provides an alternative path? Let us look at it. If we write the reaction that is catalyzed, in this case C is the catalyst, A and B are the reactants to give the product. It does not appear in the stoichiometric equation because we recover the catalyst at the end of the reaction. How it functions? The catalyst reacts with or one or both the reactants for that matter to give an intermediate compound. In this case, A plus C gives you AC, the intermediate compound. Then the intermediate compound AC reacts with other reactant B to give the product, and in the process the catalyst C is regenerated. Catalysts, based on how they are used in a reaction, can be used to classify the process of catalysis, the phenomenon of catalysis. Broadly, we classify them as homogeneous catalysis and heterogeneous catalysis, and within homogeneous catalyst the reaction can be gas phase or the liquid phase, and in the case of heterogeneous catalysis generally we use solid catalyst and the reactants can be in the gas or vapor phase or in the liquid phase. Then we have enzyme catalysis, the catalyst that the nature uses is enzymes. Enzymes are large molecules having colloidal dimensions, therefore, it does not fit in either in homogeneous catalysis or in heterogeneous catalysis, but they are too small to be visible to the naked eye. We can at the most call them micro heterogeneous catalysis, almost bordering with homogeneous catalysis. There are differences between homogeneous and heterogeneous catalysis. The first difference is that homogeneous, the term itself tells us that the catalyst and the reactants are in the same phase, and in the case of heterogeneous catalysis, the two are in different phases. The catalyst is in a different phase and the reactants are in a different phase, solid gas, solid liquid. You can see the temperature. The general temperature that is employed in homogeneous catalysis is milder, whereas we require high temperature in the case of heterogeneous catalysis. The activity of homogeneous catalyst is slightly lower than that of the heterogeneous catalyst. That is partly counterbalanced by higher selectivity that is afforded to by homogeneous catalysts, whereas here the heterogeneous catalysts slightly lag behind. But then, because of the milder conditions that are employed here in the case of homogeneous catalysis, we can use the usual probes to find out what happens during the course of the reaction, and that will give us a method to find out the mechanism of reaction, whereas it is very difficult to use the probes under the drastic conditions that we employ in the case of heterogeneous catalysis. In such cases, mechanism, the elucidation of mechanism becomes extremely difficult. What are the advantages of homogeneous catalysts? One is they have higher selectivity, that is desired. We want to get the desired product. I do not want any undesired product, side products. They can be tailor made. We can design homogeneous catalysts in some cases for a specific requirement because we have some flexibility there. Whereas in the case of heterogeneous catalyst, the main advantage is that it is easier to separate the catalyst from the reaction system after the reaction is over. It is a chemical engineering requirement so that the process can be easily carried out. In the case of homogeneous catalyst, that is a major stumbling block. After the reaction is over, it is a very difficult task to remove the homogeneous catalyst that is present in the reaction mass. In the case of heterogeneous catalysts, we have higher activity. The catalysts are very robust, and hence the industries use heterogeneous catalysts. Let us look at some examples where the catalysts are used in different states. First, look at where we have a gas phase catalyzed reaction. This is an important reaction, sulfur dioxide oxidation in presence of nitric oxide as the catalyst. The entire reactant as well as the catalyst is in the gas phase. The mechanism that is proposed is that the catalyst that is used reacts to give an intermediate product, in this case NO2, which then reacts with sulfur dioxide to give you the product SO3 plus the catalyst that is regenerated nitric oxide. Nitric oxide also can be used in the oxidation of carbon monoxide. You can see this reaction. Again, NOx, that is oxides of nitrogen, acting as catalyst. One more example we can look at it. It is a thermal decomposition of acetaldehyde. Iodine vapor acts as a catalyst, and you can see that the reactant as well as the catalyst are in the vapor phase. The rate of reaction increases several hundredfold in this particular case. Liquid phase reactions, these are very common reactions that we come across in kinetics quite often. You might have even carried out these reactions in the laboratory during kinetic experiment. Hydrolysis of methyl acetate catalyzed by, say, hydrochloric acid. Also, inversion of sucrose catalyzed by hydrogen ions. We have to prepare a solution of sucrose, add HCl and study the reaction at different concentrations of the catalyst and maybe the reactant to find out how the catalysis works in this case using a polarimeter. Solid catalyst and liquid reactants, hydrogen peroxide decomposition using platinum catalyst. It is very clear colloidal platinum can be used because that will be more effective in bringing about the catalysis. Gaseous reactants, Haber's process in which we carry out the reaction between hydrogen and nitrogen to give you ammonia, we use ion catalyst. Another important reaction is the hydrogenation of oils to produce saturated fats. Here we use Raney Nickel as the catalyst. It is an important reaction because we get edible oils from the seeds which may not taste good. In such a case, to improve the taste as well as its feel, that you can convert that into saturated fat like margarine, dalda. Once upon a time we used to hear about it. It is an important reaction industrially. Solid catalyst, solid reactant. There are not many examples of this type. It is of academic interest, but you might have come across this reaction. Decomposition of potassium chlorate in presence of manganese dioxide, both are solids. This is used in the preparation of oxygen in the lab. Characteristics of catalyzed reactions. Important characteristics are: a catalyst increases the rate of a reaction without being consumed in the reaction. We get back the catalyst. If I use 1 gram of platinum, I get back 1 gram for it. A catalyst takes part in the reaction and may undergo a physical change but remains chemically unchanged. Yes, the platinum catalyst that you use, which is a shiny smooth metal, is recovered in the form of a coarse dull metal, clearly telling us that there is something happening to the catalyst, and this is because of the fact that it takes part in the reaction. Only a small amount of catalyst is sufficient, right, because it is not consumed, and you have the example 1 gram of platinum used as the catalyst for the decomposition of hydrogen peroxide. It can bring about reaction of a very large volume, 10 raised to 6 liters of hydrogen peroxide. The catalyst does not initiate a reaction. Yes, thermodynamically catalyst does not contribute, it does not change the thermodynamics of the reaction. If the reaction takes place, catalyst can increase the rate. If the reaction does not take place, thermodynamics says no, then catalyst cannot do in this case. A catalyst does not alter the position of equilibrium. As I told you, it does not contribute energetically to the reaction. It only provides an alternative path from the initial state to the final state, and therefore, the equilibrium position remains the same whether a catalyst is used or not. Catalyst only increases the rate at which the equilibrium is reached. Therefore, a catalyst that is suitable for the forward reaction should be equally suitable for the reverse reaction, because we know that capital K, the equilibrium constant, is equal to K1 divided by K2, where K1 is the rate constant for the forward reaction and K2 is the rate constant for the reverse reaction. A catalyst is specific in its action. Yes, the catalyst is specific in the sense that it will only catalyze a particular reaction. It may not act as a catalyst for any other reaction. There is nothing like a universal catalyst. Actually, if it is specific, then you cannot have a catalyst which works for all types of reactions. Catalyst does not alter the nature of the product of the reaction. Look at this. Ethanol vapor, when passed over alumina, gives you an olefin. But this reaction shows that the product has altered. But actually what happens is, these reactions are complex reactions. There is a distribution of product that is coming out, and the catalyst may catalyze a particular step, leading to an appearance that the product has changed. Actually, that does not happen. There is an optimum temperature for every catalyst at which its activity is maximum. And if we want to increase the rate of or activity of the catalyst, we can add certain substances which, when added, increase the activity of the catalyst. Such substances are called catalyst promoters. These promoters are not catalysts by themselves, they cannot catalyze the reaction, but in conjunction with the catalyst, they can increase the activity of the catalyst. And there are certain other substances which, when added to the reaction system, acts as poisons. They destroy the activity of the catalyst. Theories of catalysis. The first theory is intermediate compound theory, which we will be looking at in this lecture. A catalyst will react with one or more of the reactants to form an intermediate compound, which we have mentioned earlier, which then reacts with the other reactant to give the product, and in the process the catalyst is regenerated. You can look at this. This is exactly what we saw in describing an alternative path that the catalyst provides. What is the proof? Look at this. The same shiny smooth platinum recovered as dull and coarse. The best example is provided by decomposition of potassium chlorate catalyzed by manganese dioxide. In this particular case, oxygen is obtained, but where is the proof that manganese dioxide takes part in the reaction? The coarse granules used as the catalyst of manganese dioxide are recovered in the fine form. Why the particle size should change if it does not take part in the reaction? But further proof can be obtained. Oxygen that is prepared by this method is found to contain traces of chlorine. From where chlorine comes? The reaction mixture appears pink. From where this pink color appears? So, we have to now propose a mechanism which tries to explain this. What manganese dioxide does? It must be reacting. It must be reacting with potassium chlorate to give potassium permanganate as an intermediate compound, which gives pink color to the reaction mixture initially. In the same reaction, chlorine is also formed. You can see chlorine is formed. Therefore, the oxygen prepared is contaminated with traces of chlorine. But both of these are consumed in the subsequent steps, whereby the manganese dioxide which is reacting here is regenerated, and the intermediate compounds do not appear in the overall stoichiometric equation. We get the product oxygen there. Let me summarize what we discussed today. I introduced you to the topic of catalysis. The term was coined by Berzelius in 1830s. The Chinese term for catalyst is Zhu-Mi, which means marriage broker. It exactly does that job, brings the reactants together to form the product, facilitates the product formation. What is a catalyst by definition? A catalyst is a substance which increases the rate of a chemical reaction without being consumed in the reaction. It may undergo a physical change, but it remains chemically unchanged. Classification of catalysis. Catalysis based on the phases we can classify as homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis is the one in which the catalyst and the reactant are in the same phase, whereas heterogeneous catalysis, the catalyst and the reactants are in different phases. Each one of them have their own advantages. Some examples of homogeneous catalysis we have seen, in which all the catalyst as well as the reactants are in the gas phase. We have seen examples in which the catalyst and the reactants are in the liquid phase. Heterogeneous catalysis is the one in which the reactant and the catalyst are in different phases. We have seen the examples, Haber's process. We have seen that nitrogen and hydrogen combine together to give ammonia in presence of iron catalyst. Iron catalyst is solid, it is a formulation containing iron as the principal component. And then we have looked at the basic theory that is proposed to explain how a catalyst functions, intermediate compound theory. The essence of the theory is that the catalyst reacts with one or more of the reactant to give an intermediate compound. This compound then reacts with the other reactant, or it decomposes to give the product, and the catalyst is regenerated at the end of reaction. So that's all we have for today's lecture. We will continue with the other theory, important theory, adsorption theory, which tries to explain heterogeneous